Okay, so with that, Joachim, the floor is yours.
Okay, thank you very much. So yeah, also from my side, welcome to the second day of the school. Congratulations to all the Italians in the audience, and sorry to all the Spanish in the audience. So today our topic will be neutrino mixing and oscillation. So remember, on Monday we discussed how neutrino masses can arise, and I promised to still show you some slides to discuss the relevant experiments, but I might only be doing that tomorrow because the topic today is a relatively long one, and I don't want to break it up across lectures. So I'm first going to talk with you about neutrino mixing and oscillations, and then if we still have time today at the end, we're going to look at the pictures, and if not, we're going to do it first thing tomorrow. Okay. To begin and to remind ourselves what neutrino mixing is, let's first look once again at the Lagrangian of neutrinos. So that's going to be subsection 2.1, 3 flavors of neutrinos. Yeah, so we already discussed in the first lecture that the way neutrinos interact is, on the one hand, there is, of course, their kinetic term. So all of this appears under a sum over flavors. Nu alpha left bar d slash nu alpha left. That's just the kinetic term. There is the coupling to the W bosons, G divided by square root 2 times W mu alpha L gamma mu E alpha L plus Hermitian conjugate. So here, notice once again that the flavor index on the neutrino and on the charged lepton is the same, and that's basically what defines the flavor of the neutrino. So the electron neutrino is by definition the neutrino that couples together with the electron to a W. Finally, there is the term that couples neutrinos to the Z boson. It has the structure G divided by cosine theta W, Z mu alpha L bar gamma mu alpha L. And now, since we've now discussed neutrino masses, we can write out the mass term explicitly. Let's choose for illustration a Majorana mass term. It has a sum over 2 flavor indices with a 1/2 m alpha beta nu alpha L charge conjugate bar times nu beta L plus the Hermitian conjugate. Right. Now these m alpha beta, they form a matrix. And in general, this is, of course, an off-diagonal matrix. There's no reason to restrict this to the diagonal, so it can have non-zero off-diagonal entries. So m alpha beta, this matrix is in general off-diagonal. So that means that through these mass terms, different neutrino flavors talk to each other. And that's in fact the only way in which different neutrino flavors talk to each other. Now, in order to compute Feynman diagrams, in order to compute how neutrinos propagate, it's advantageous to diagonalize the mass matrix, because the propagation of a particle is determined by its kinematics, and its kinematics are determined by its mass. So for that purpose, we need to go to quantum states of definite mass. And that's done by diagonalizing this mass matrix. And of course, we do so at the expense of now introducing off-diagonality in the gauge couplings. Okay, so this diagonalization is achieved by writing nu alpha L as some matrix U alpha J times nu J. So nu alpha L are the flavor eigenstates as before. this U alpha J here, that's what's called the mixing matrix. And it's just the lepton analog to the CKM matrix. In the lepton sector, it's often called the PMNS or Pontecorvo-Maki-Nakagara-Sakawa matrix. And these new J here, so these are the neutrino mass eigenstates. So these are the states of definite mass. And the two types of states, the flavor states and the mass states, are related by this unitary matrix. These are the flavor states. And let's write out explicitly here that this mixing matrix is unitary, because of course this transformation should not violate particle number conservation. So in order to make sure that this matrix U actually diagonalizes M, we need to ensure that it has the property that nu alpha, that it has the property that U transpose times M times U is a diagonal matrix. So diag of M1, M2, M3. Right? Notice that this here is a U transpose, not a U dagger. That's because we are working with a Majorana mass term. So if you apply this transformation to nu and to the charge conjugate of nu, then you end up with U and U transpose rather than U and U dagger. And therefore, this is the transformation that needs to diagonalize the mass matrix.
Joachim, can I interrupt you?
Sure.
There was a question in the chat by Simone.
Please go ahead.
So are the new J fields left-handed fields? So the mass eigenstates that you
Yes, they're also left-handed. I should probably indicate this here. So let's give them a subscript L as well. Yeah, so handedness determines how the field transforms under the Lorentz group, and doing a unitary mixing between different left-handed fields retains the left-handedness. So the transformation we are doing here does not change the transformation properties under Lorentz transformation. So they are also left-handed. So in order for, of course, not every matrix can be diagonalized in this way. So in order for this to work, the matrix must be symmetric. And we argued already last time that it's symmetric anyway for symmetry reasons. So for this to work, or no, let's say it differently. Let's say this only works because M alpha beta is symmetric. It can be complex, but it has symmetric. It has to be symmetric, not Hermitian, but symmetric. Okay, so this transformation is the one that moves between flavor eigenstates and mass eigenstates. So that's one of the central relations to neutrino mixing physics. This one here.
Joachim, there's another question.
Please go ahead.
So Jamie is asking, why isn't there a right-handed kinetic term?
In principle, there should be, but at this moment, I haven't introduced right-handed neutrinos yet, right? I'm working here with a Majorana mass term. So imagine, for instance, that we are in the seesaw picture. So we've integrated out the right-handed neutrinos because they are very heavy and don't affect the phenomenology directly. So they can't be produced in a conventional experiment. So if they are dynamical degrees of freedom, then of course also their mass term should be there. But the way I've written it here, I'm working in an effective theory that only includes the left-handed neutrinos.
And there's a question which is maybe a follow-up by Arman.
Yeah.
Are these mixing relationships also valid for the right-handed neutrinos? No,
the right-handed neutrinos have a separate mixing relationship. So in principle, the mixings of the left and right-handed ones do not need to be related. Also, when you do this in the quark sector, for instance, the matrix you use to transform the left-handed fields is different from the matrix you use to transform the right-handed fields. That's similar in the neutrino sector. However, for the right-handed neutrinos, there isn't really a definition of a flavor basis. Because remember, the way we defined the flavor basis was precisely by looking at how the neutrinos couple. So the flavor basis is defined by which charged lepton each neutrino couples to. Now, the right-handed neutrinos don't couple to charged leptons. So there isn't any particular interaction basis that would be better than the others. So for the right-handed neutrinos, it's conventional to just always work in the mass basis.
Thanks.
Okay, so note that what we did here was for Majorana neutrinos. So let me quickly mention what would happen in the case of Dirac neutrinos. So for Dirac neutrinos, the situation is actually much more similar to the quark sector. So for Dirac nu, the mass term would read, it would be a sum alpha beta m alpha beta nu alpha L bar nu beta right. So now here the right-handed neutrinos become physical. And in that case, the transformation is a different one for left and right-handed fields. So the left-handed ones will then transform as nu L alpha equals U alpha J times nu J. And the right-handed ones will have a different transformation with, say, a matrix V beta J times nu, okay, let's call this one nu JR and this one nu J left, because now, of course, also we need to distinguish the handedness of the right-handed states. And in that case, the relation for diagonalizing the matrix is that U dagger times M times V is equal to diag of M1, M2, M3. And this works for a general complex M. Works for general complex M alpha beta. So this restriction that the mass matrix is symmetric, it is not there in the Dirac case, but also because we now have independent transformations for the left and right-handed particles, we have more freedom in diagonalizing the matrix. So it is diagonalized by multiplying by a different matrix from the left and from the right. And in fact, even though we call these M1, M2, M3, usually the mass eigenvalues, this is not really an eigenvalue transformation. That's a singular value decomposition. But as the physicists usually are a bit sloppy with their notation. But strictly speaking, what we are doing is not an eigenvalue calculation. That matrix may not be diagonalizable in the linear algebra sense, but it can always be decomposed using what's called a singular value decomposition. Okay, so that's just as a side remark about what happens for Dirac neutrinos. For the rest of our discussion, it doesn't really matter whether we have a Dirac or a neutrino mass or a Majorana neutrino mass term, because in the following, we will only be interested in what happens to the left-handed neutrinos, because those are the only ones that we can detect experimentally. So now doing this transformation to the Lagrangian, the latter can be written in the following way. So in the mass basis, the Lagrangian now looks as follows. There's now not a sum over flavor eigenstates, there's a sum over mass eigenstates. Of course, each mass eigenstate has a kinetic term. So that's what we simply obtain by transforming the kinetic term from the mass basis to the flavor basis by using this relation here. The term that couples the neutrino to the W boson is the one that suffers the most important modification. So this term now reads G divided by square root 2 times W mu times nu alpha, nu J left bar. times a mixing matrix element, U alpha J star. That's new. So that's basically rewriting the new alpha field from before in terms of this. And also here for this term, the sum, sorry, I should have written this differently. So the sum here now for this one is over flavor. The gamma mu stays where it is, and the charged lepton field also stays where it is, because obviously the charged leptons, for them by definition, flavor and mass eigenbases are the same. So this is the term that suffers the most important change. Then the term that couples the neutrinos to the Z boson again looks very similar to before. There's a sum over J, Z mu, nu JL bar, gamma mu, nu JL. Here, once again, because there are two neutrino fields, the two mixing matrix insertions from the transformation of this one and of this one cancel. And finally, there's the mass term, which is now diagonal. So sum over J, 1/2 mj times nu J left, charge conjugate bar, times nu J left. So as I said, the most important modification happens to the charged current interaction term, this one here, because this one now contains this mixing matrix insertion. So the way this can be interpreted is that a charged current neutrino interaction produces a superposition of mass eigenstates. So a charged current nu interaction involves a superposition of mass eigenstates. Involves superposition of mass eigenstates. So diagrammatically, for instance, when a W boson decays to a neutrino and a charged lepton, there is now three diagrams. There is a diagram where we go to an electron and a new one, plus the diagram where we go to an electron and a new two, plus a diagram where we go to an electron and a new three. So this here is always the W boson, and the coupling here is given by G over square root 2 times a mixing matrix element. So here this is UE1 star. Here it's G divided by square root 2 times UE2 star. And over here it's G over square root 2 times UE3 star. So that's what I mean by producing a superposition. Now the thing is, since the masses of nu1 and nu2 and nu3 are so similar, the three mass eigenstates can't easily be distinguished. If this was a decay to particles of vastly different masses, then the kinematics for the three decay modes would be vastly different, and we could simply from kinematics determine exactly which state has been produced. But because neutrino masses are so similar, all of them extremely tiny, with small differences between, therefore we cannot easily distinguish experimentally which mass eigenstate was produced, and that's why we can see the quantum mechanical interference effects. And the way we see them is via neutrino oscillations. So now let's talk about how neutrino oscillations occur. So I'm going to discuss this here using a formalism mostly based on quantum mechanics, and I'm then going to comment in the end on how this could be done more properly in quantum field theory. So the starting point for neutrino oscillations is, well, that we make a neutrino. So a neutrino is produced in a charged current interaction. And in that, it's produced together with a charged lepton. So produced in CC interaction. So the neutrino is produced as a flavor eigenstate, meaning as such a superposition of mass eigenstates as I showed here. And that superposition quantum mechanically can be written as state nu alpha equal to u alpha j star times mass eigenstate nu j. So the summation over j is implied here. So from now on, I'm going to use the Einstein summation convention. Right? So that's just saying once again what I have shown diagrammatically above. Now, when the neutrino is detected, the detection typically occurs to a charged current process again. And the detection happens because then the neutrino produces a charged lepton, and we identify the flavor of the charged lepton. So CC detection. Maps the neutrino state onto a flavor eigenstate. Onto flavor eigenstate nu beta, or let's we'll need it as a bra vector, not as a ket vector, so let's write it as a bra vector right away. Nu beta is equal to u beta j times nu j. Because I'm writing it as a bra vector, so as a Hermitian conjugate of a ket vector, there is now no complex conjugate on the matrix element. So neutrino oscillations are something that occur between production and detection. So in order to compute the amplitude for neutrino oscillations, we need to take the produced neutrino state nu alpha. We need to evolve it in time. I'm going to denote this here as nu alpha of t. And we need to project it back onto nu beta. Let's do this explicitly. There is from the nu alpha, there is a mixing matrix element u alpha j star. From the nu beta, I get a mixing matrix element u beta j. And there is the propagation. Propagation is determined by the neutrino's energy, and the energy is in general different for different mass eigenstates. So each mass eigenstate upon propagation acquires a phase factor of the form e to the minus I ej times time plus I pj times L. So that's just how a quantum mechanical state evolves in time and space, right? It's just, for the moment, we are working here with plane wave states, and this is how a plane wave state evolves in space and time. So this here is time and space evolution of quantum mechanical plane wave state. All right. So you see that we now have interference terms. So for when we square this, we will get terms in which different mass eigenstates contribute with different phase factors. So let's write this down. The probability for a flavor conversion, so the probability, for instance, for a nu alpha converting to a nu beta after propagation is the amplitude squared. And doing this, we now get two sums over mass eigenstates. So we get a sum over J and a sum over K. We get four mixing matrix element U alpha star U beta J from A, and then A square here is A times A complex conjugate. So from the complex conjugate, we get U alpha K times U beta K star. Then we get the complex phase factor, which now reads e to the minus I ej minus ek times t plus I times Pj minus Pk times L. And this is what I meant by interference term. So here we now see this interference. So wherever there's interference, we expect oscillatory phenomena. And indeed, that's where neutrino oscillations are coming from. We'll see this more explicitly shortly. At this point, however, I first would like to make one comment. Namely, you see that I give the energy and the momentum an index J here. And that's justified because different masses have lead to different kinematics. So the energies and momenta of different neutrino mass eigenstates should be different. Now, you may wonder, how can they then interfere? Because in principle, states with different energies, these are different states in a Hilbert space. So how can they interfere with one another? Like when I project one of them onto the other, I get zero because they're different states in a Hilbert space. However, what comes to the rescue here is that the energies and momenta of the different mass eigenstates differ by only a very small amount. In particular, they differ by an amount that is smaller than the Heisenberg uncertainty on the energy and the momentum. And therefore, interference is nevertheless possible. So let's write this down. Note. States with different E and P. Can interfere only if the E and P uncertainties are larger than the energy and momentum differences. Are larger than EJ minus EK and PJ minus PK. And fortunately, that's always the case in realistic neutrino experiments. There's a relatively easy way to see this, just from the fact that we have a rough idea of where in space our detector is located and where in space our source is located. That already implies that the spatial uncertainty of the neutrino production point must be smaller than a certain value. And then by the Heisenberg principle, the momentum uncertainty must be larger than a certain value. And this localization of the neutrino production point is already enough to introduce an energy and momentum uncertainty that's large enough to ensure that interference is possible. So if you don't want to make this somewhat hand-wavy argument about the Heisenberg principle, the whole calculation could also be done in a wave packet formalism, but I'm going to comment on this in a moment. So a wave packet formalism is basically a way to formalize the uncertainties in the external states, but I'm going to comment on this in a moment. Now let's first proceed here and try to get this oscillation probability into a somewhat nicer form. And the first simplification we can do here is, you see here that there is still a time dependence and a space dependence. Now, this time dependence is usually irrelevant. And that's because we can't measure the neutrino's propagation time sufficiently accurately. So typically, we do not know T precisely. Because the uncertainty in the neutrino production time is much larger than the typical energy differences. So EJ minus EK to the -1. And that means that by integrating over all possible neutrino production times in my uncertainty window for T, I'm integrating over many, many oscillations of this first exponential factor here. So I can, to a very good approximation, simply do an integral from 0 to infinity. So therefore, the observable oscillation probability can be written as, so let's call this P bar, for instance, which is integral dt a squared. And we need a normalization factor to make sure this is still a probability. So doing this integral and doing it over an infinite interval, which, as I said, is justified as long as the integral is over many, many oscillations of this function, well, we obtain just a delta function. A delta function that ensures that EJ is equal to EK, meaning that effectively, within the uncertainty window, only those states in which EJ is equal to EK interfere. PJ and PK may still be different, of course, because the masses are different. So we end up with a sum 1 over this normalization factor, sum over JK. These are now just the 4 matrix elements, which I'm going to copy from above: U alpha J star, U beta J, U alpha K, U beta J star. The energy conserving delta function reads 2 pi times delta EJ minus EK. And the remaining exponential now has the structure. Let's write out the momenta explicitly now. So the momentum is now I times square root E square minus MJ square minus square root E square minus MK square times L. The delta function and the factor of 2 pi can be absorbed into the normalization here. Don't be shocked by the fact that we are assuming a formally infinite quantity into the normalization factor. This is a bit sloppy, I have to admit, but as I said, I'm going to explain you in a moment how to do this in a more formal way using quantum field theory, and then all of these this sloppiness would disappear. But before we do this, let's make one last approximation. So here, this exponential here can be approximated by using the fact that neutrino masses are extremely small. So this here is approximately equal to exponential of minus I times delta M J K squared divided by 2E times L. And this delta MJK square, that's a quantity that appears all the time in neutrino oscillation physics. It's the difference of the squared masses. So it's just, by definition, MJ square minus MK square. So all I've done here is I've Taylor expanded the square roots here for small MJ.
Joachim, there was another question related to something a little earlier by Gonzalo. Why is there a conjugate in the U matrix when relating the quantum states, but not for the mixing of the original fields?
The reason is, if you remember how a quantum state is defined. So I'm going to write this now and then or maybe let's keep this as a side note here. So a state nu alpha in quantum field theory is essentially defined by a creation operator times the vacuum, right? Now the creation operator is the one that appears in the conjugate field. So if you look at the new field, nu alpha, that's some integral d3p divided by 2 pi cube times 2e times an antiparticle creation operator times e to the ipx minus a particle annihilation operator times e to the minus ipx. So in order to obtain a particle state, I need to act with the conjugate neutrino field on the vacuum. And this conjugation, this is what introduces the star on the mixing matrix.
Thanks.
Okay. So the expression that I've written down above, this is the most general way of writing down the neutrino oscillation probability. However, for many practical applications, it's instructive to simplify this even further by considering a two-flavor system only. So if we consider only two neutrino flavors, an approximation which is quite reasonable for many types of experiments, then the mixing matrix is just a 2x2 matrix. So before I said that this U is a general complex, a general unitary 3x3 matrix. So a general unitary 3x3 matrix has a number of parameters. But if it's only a 2x2 matrix, then it can be parameterized in terms of a single mixing angle. So a general unitary 2x2 matrix can be written as cos theta, sine theta, minus sine theta, cos theta, where theta is some mixing angle. And with that, the oscillation probability can be simplified in the following way. I'm just going to give you the final result because it's really just a matter of inserting this mixing matrix up here in the general expression. So P alpha beta is approximately equal to, in the two flavor regime, to sine square 2 theta times sine square delta m square L over 4e. I'm not putting the indices on the delta m square anymore because now there is only two mass eigenstates in the two flavor limit, and so there is only one possible difference. Okay, so that's the expression for neutrino oscillations that you will most often work with to get a rough idea of what's happening. So what's interesting here is there are two terms here. The first one here is just a constant. It depends on the mixing angle, so on a fundamental parameter of nature. The second one here is the one that oscillates in space. So the first one here essentially determines the oscillation amplitude. So in other words, the larger the mixing angle is, the larger the oscillation amplitude is. If the mixing angle is very, very, very small, then only very few nu alpha will convert into nu beta. If the mixing angle is large, then even a full conversion between nu alpha and beta may happen. The conversion is largest if theta is 45 degrees, because in that case, 2 theta is 90 degrees and sine of 90 degrees is 1. So in that case, we will have full conversion from nu alpha into nu beta and back again. And this actual oscillatory behavior is described by the second term here. So this is the actual oscillation term. And it describes oscillations that happen over distance scales given by 4e over delta m square. So this is typically defined as the oscillation length, which is by definition where delta m square L over 4e is equal, So the oscillation length is defined as the distance over which this phase factor equals pi. So in other words, the oscillation length is 4 pi e divided by delta m squared. So in other words, the mixing angle is the parameter that determines the amplitude of the oscillations. The mass squared difference is the parameter that determines the distances over which oscillations develop. So mixing angle theta controls oscillation amplitude. And delta m square controls oscillation length. Okay. So far, so good. Now, I promised to tell you a little bit about how this formalism can be improved in quantum field theory. So in QFT, neutrino oscillations can be described by the following diagram. Or let's say by a diagram, by a Feynman diagram of the following type. So the neutrino production process involves, for instance, an up quark going to a down quark, emitting a W boson. The W boson goes to a charged lepton. So let's call it an electron, for instance, and a neutrino. Now I'm drawing the neutrino line very, very long here because the neutrino is traveling over a macroscopic distance. And then somewhere on the other end, there's again an interaction with a W boson and a charged lepton, converting, for instance, a down quark to an up quark, like this. And once again, emitting a charged lepton. So the part on the left here, that's the neutrino production process. This is new production. And the part on the right here, this is the neutrino detection. And in principle, this diagram can be calculated. The neutrino propagator here is a bit unusual in the sense that it is supposed to be a propagator over macroscopic distances. And so it will receive essentially only contributions from neutrinos that are on shell. So here in between, there's a macroscopic distance L. And now, in order to specify where the neutrino production and where the neutrino detection happen, the way this is done is by treating the external particles using wave packets. So treat all external particles as wave packets. So in other words, what you do is you compute the amplitude for this diagram, or you write it down in momentum space, but then you fold it with the wave packet shape for each of the external particles. And then you have lots of Gaussian, if you assume the wave packets to be Gaussian, you have lots of Gaussian integrals to solve, but because they are all Gaussian, this can be done. And then you quite naturally end up with an expression for the oscillation rate that is the same as the one we found above. But now you don't have any complications with having to invoke the Heisenberg principle. That's all automatically taken care of by the wave packet formalism. You don't have problems with having to absorb some infinities into some normalization factor. That's also much more formalized in quantum field theory. So basically, a more complete derivation of neutrino oscillations would amount to evaluating this diagram here. But that would be a few pages of algebra, and therefore, obviously, we won't have time to do so today. Okay, what we do, however, have time for is to go beyond the two flavor case. So obviously neutrinos do not exist in two flavors in nature, they exist in three flavors. So we have to think about at least how to parameterize the situation in three flavors.
Joachim, there's a question coming in right now. What is the, so this is a question by Xurun, I hope I pronounce this correctly. What is the case if the production or detection is by neutral current channels? Anything different or just the same as charge current?
That's, I think, one of the exercise problems I set, and therefore I'd like to postpone this to the discussion session. It's a very interesting question and there is an answer to it. But actually, I would like everyone to maybe who likes to actually have a think about it. And then let's maybe discuss it tonight in the discussion session at 4:30, okay?
Sounds good.
Okay, so let's talk about the three flavor system. So three flavor oscillations. The basic difference in three flavors is that, well, now we are dealing with a 3x3 unitary matrix. And now let me see into how much detail I want to go on this, or if I should rather still discuss neutrino matter effects. I think it's more important that I discuss neutrino matter effects. So here I'm just going to tell you what the mixing matrix looks like in the three flavor case. So the mixing matrix is a unitary 3x3 matrix now. And the general parameterization of such a matrix is the following. It's written as the product of three rotation matrices, one of which also includes a complex phase. So we conventionally write it as a rotation in the 2-3 plane, where these S and C, so S2, 3 here stands for sine of theta 2-3, and theta 2-3 is one of the fundamental parameters of this matrix. So that's a parameter that has to be determined experimentally. And C2-3 is correspondingly the cosine. There is a rotation in the 1-3 plane, and that's the one that's assigned, has a complex phase factor attached. Once again, that's a fundamental parameter of nature that needs to be determined experimentally. Okay, here 0, 0, 0, 0, and C13. And finally, a rotation in the 1-2 plane, C12, S12, minus S12, C12, 1. Now, you may wonder, why is this the most general parameterization? In principle, there should be additional factors. However, many of the phases that would appear in a general unitary matrix can be absorbed into a redefinition of the quantum fields. So if I had an extra phase factor appearing in my Lagrangian that, for instance, always multiplies the new 1 field, then I can simply redefine the new 1 field to absorb this phase factor. And that has already been done here. And it can be done because overall phase factors don't affect physics. So where some phase factors, or where, let's just say where phase factors, basically all possible phase factors, have already been absorbed into the definition of the states. Have been absorbed into redefinitions of states. Okay, now I see that I have about 10 minutes left, and in those 10 minutes, I would like to talk about what happens when neutrinos do not propagate through vacuum, but through matter.
Joachim, there's one question by Simone.
Please.
So in this parameterization, have we absorbed the Majorana phases in this parameterization yet?
No, the Majorana phase, well, if neutrinos are Majorana, then fewer phases can be absorbed than if they are Dirac. This can be seen actually from the structure of the mass term. Where was it? So here in a Majorana mass term, you have the left-handed fields appearing both on the left-hand side and on the right-hand side of the mixing matrix. So you have only 3 fields available into which you can absorb an overall phase. For a Dirac mass term, you have left and right-handed fields. You have more fields available to absorb phases into, so you can absorb more phases. However, even if there are Majorana phases that cannot be absorbed, I haven't written them out here because they would drop out of the oscillation probabilities. And that's because if you look at the general expression for the oscillation probability, it contains these 4 mixing matrix elements here. And the Majorana phases, they appear on the diagonal of the mixing matrix. So in the diagonal entries, each of the diagonal entries in this horrible sum here appears always together with its complex conjugate. So if there are Majorana phases, they would cancel each other in this combination of matrix elements. And therefore, neutrino oscillations are always completely insensitive to Majorana phases. And that's why I have not explicitly written them out here. But in principle, if neutrinos were Majorana, then there should be 2 extra phase factors here.
Thank you. And then there was one more question on Slack from Aman. Why are we choosing this particular rotation? I guess this is relating to the form that you write out the U matrix here.
It's a convention. There's really no better reason to it than to say it's a convention. Like choosing the order of the rotations differently would be equally valid. If you think about the quark sector, for instance, there's a number of different parametrizations of the CKM matrix, each of them suitable for different purposes. And in principle, we could do the same also in the neutrino sector. It's just that somehow the community has agreed that this is the parameterization we're going to use.
Okay, thank you.
Okay, so in the last few minutes, let me at least start by talking about neutrino oscillations in matter. Because when neutrinos travel through matter, something quite interesting happens. And the interesting thing that happens is that, well, neutrinos can interact with the particles in the matter they are traveling through. Now, you know that neutrino scattering cross-sections are extremely tiny. So in order to stop a neutrino efficiently, you would need a slab of lead that is as big as the diameter of our galaxy. So you may wonder, okay, why do neutrinos even know that they are traveling through matter? And the reason they do is related to a process called coherent forward scattering. So how does this work? Diagrammatically, imagine you have a neutrino traveling here, and the neutrino is scattering on some background particle. So this could, for instance, be a proton or a neutron or an electron that of the matter that the neutrino is traveling through. So let's call this a background particle. And now the neutrino can interchange, for instance, a Z boson here. So let's assume that this is a Z, for instance. Here's the incoming neutrino, the outgoing neutrino. Now, if the neutrino experiences a momentum change in this scattering, well, then indeed the scattering cross-section is extremely tiny. However, there is the possibility that as this scattering happens, the neutrino and the background particle do exchange a Z boson, but the neutrino retains its momentum. So in a sense, there is no momentum exchange, even though there is an exchange of a Z boson. And in that case, the following happens. Typically, there isn't one background particle, there is many, many, many of them, right? Because we are traveling through ordinary matter, which has 10 to the 23 particles per cubic centimeter. And in that case, we cannot tell on which of the background particles the scattering has happened. So in a sense, there is another diagram where, so if here, I need to make sure I get the same number of background particles. There is a similar diagram where the neutrino scatters on another background particle. And there is a diagram where it scatters on the fourth background particle. And all these diagrams need to be summed up. And they need to be summed up coherently because there's no momentum exchange. So we have no way of telling on which of these background particles the scattering has occurred. And this is what leads to a huge enhancement to this forward scattering rate. So exchange of W or Z boson without momentum change means that all background particles contribute coherently. There's actually an analogy to this, namely photons traveling through a material. So when a photon travels through water, for instance, the photon can interact with each individual water molecule, but we can't tell which one it interacted with. So we can only see the integrated effect. And that's what we call a refractive index then. And similarly, also neutrinos experience a refractive index when traveling through a medium. So because of this coherent summation, we now find that let's say the squared matrix element for this process is now proportional to n square times the Fermi constant square. So the scattering on an individual particle is the Fermi constant square. If this was an incoherent scattering process, we would have to sum incoherently over all scatterers. So we would have only one factor of n here. But because they add up coherently, we get a factor of n square. So n here is the number density of background particles, density of scatterers, And really the crucial point here is that there is a square up here.
Joachim, there are two questions which I think are related, so I will read them back to back. So yeah. Teresa is asking, how is there an exchange of a Z particle without a change in the kinematics of the neutrino? And Emil is asking, does scattering with no momentum transfer not violate momentum conservation, since the mediator must carry some momentum as it is absorbed?
It doesn't need to carry any momentum. Remember that in a Feynman propagator, we are integrating over all possible momenta, including the zero momentum. So it's perfectly okay to have an exchange of a particle that does not carry any momentum. Of course, a Z boson that doesn't carry any momentum is heavily off-shell, but so be it. Scattering through off-shell particles is perfectly possible. So it sounds a bit counterintuitive, but there's nothing fundamentally wrong with it.
Thank you.
And actually, I also see that my time is up. So I'm wondering if it's maybe better to continue tomorrow. Yeah, I think.
If you want to have 5 more minutes, I guess that's fine. But
okay, then I will still talk about the basic idea and then do the equations tomorrow. Right. So we've seen that there is this enhancement because there is this square here. Now, there is one point I should still clarify. I said here, this could be an exchange of a W boson or a Z boson. Now, for a Z boson, it's clear what's happening, right? A neutrino comes in, a neutrino goes out, a Z boson is exchanged, and then couples on the other side. It can couple to an electron, a proton, or a neutron, because those are the particles that exist in ordinary matter. So that's just a relatively straightforward diagram. But a W boson, a W exchange, is usually associated with a change, with a charged current. So with a change of a particle's identity. So why can this also lead to coherent forward scattering? And the answer is it can only lead to coherent forward scattering if there is an electron neutrino scattering on an electron. So the relevant process here is this one here. An electron neutrino is coming in. That's a very ugly new E. An electron neutrino is coming in. An electron is going out. There's an exchange of a W boson. So over here it was a Z boson. I should write this out explicitly. And on the bottom end of the diagram, we have an electron coming in and an electron neutrino going out. So in this case, there is actually a momentum exchange through the W boson. But for coherent forward scattering, the momentum exchange is such that the incoming electron state down here is identical to the outgoing electron state up there. And the incoming neutrino state up here is identical to the outgoing neutrino state down there. In that case, there's once again no possible way that we can determine that the scattering has happened on this particular electron. So the quantum states of incoming particles are identical to those of the outgoing particles for coherent forward scattering. That's basically the definition of coherent forward scattering, or coherent forward scattering. And now you see something quite interesting here. Namely, the process on the left here, this works for any neutrino flavor. So for any new flavor. What's happening? Sorry about that. So for any new alpha, whereas this one here works only for new E. So in other words, different neutrino flavors will experience the presence of background matter in different ways. And that's going to be crucial for how their propagation is affected, because now it means that the propagation of different flavors is affected differently. Remember that I said earlier when we discussed oscillations in vacuum, that to describe the propagation of a particle, we need to work in the mass basis. Here now, we have an effect that affects the propagation of neutrinos, but does so in the flavor basis. And how to deal with that is something we are going to talk about at the beginning of tomorrow's lecture. Then we are going to look a bit at the experiments that I used to measure neutrino oscillations. I'm also going to show you the slides I wanted to show on Monday. And in the end, we're going to talk about the possible existence of additional neutrino flavors, so-called sterile neutrinos. Okay, but with that, I'm going to end for today. Thank you for your attention and your questions. And yeah, I'll also move over to GatherTown now for more questions, or we can still have some here on Zoom if you want.
Great, thank you, Joachim. That was a really great lecture. There's one question here by Jamie, and then we should maybe move to the coffee session. So Jamie is asking, and what happens to interactions where neutrinos change their momentum? Can't those neutrinos be also detected?
They can, but the rate for this to happen is extremely small. So in a sense, imagine that you have a neutrino source somewhere a few hundred kilometers away, and you have your neutrino detector. Then if a neutrino experiences a scattering process with momentum exchange along the way, then typically that neutrino will simply be scattered out of its way. It will never reach your detector. And even if it does, so if the scattering is relatively soft, well, you will not really see the difference. You might see a minuscule modification to your energy spectrum because neutrinos are scattered towards lower energies. But for a practical oscillation experiment that operates at order GeV energies, that effect is totally negligible. And notice also that this scattering, it doesn't do anything to the neutrino flavor, so your flavor measurement will be unaffected. The energy measurement may be affected, but only if the neutrinos are so high in energy that the absorption cross-section is huge. There is, for instance, a nice paper by the IceCube collaboration where they observe this effect in the Earth, because IceCube is observing neutrinos that have maybe several hundred TeV, and at that energy, the Earth becomes opaque to neutrinos. And so you can nicely see this absorption effect. But for experiments that look for oscillations, they operate at energies that are so low that absorption is irrelevant.
Okay, thank you, Joachim. Yeah, let's thank Joachim for this great lecture. And we can now go to Gather Town for our coffee break. And since we are running a little bit over time, we will start a little later at 11:22. So this is basically giving us a 15-minute break. Okay, thank you very much and see you soon. We will leave the Zoom room open during the coffee break.